And then this negative 1 is going to go to its origin, which is the len of the absolute of the x plus c, such that c is a constant, the integration constant. This is the simple rule, or the simple version of that rule. What if we have a full function? Here, if we have a function in the denominator and its derivative is in the numerator, this equation as a function and it's raised all of the bracket to the power of negative 1. If it's multiplied with the derivative of what inside the bracket, so we ignore the power of 1 and we look for the derivative of what's inside the bracket. If it exists inside the integral, then we can say that this was the derivative of len absolute or modulus of the function plus the integral constant. So this is the general case of the logarithmic. We can call this the simple logarithmic integral, and this is the general form for any function. Of course, the simple is derived from the general form of the logarithmic integral, but we can deal with them in two phases. Okay, so let's take from the sheet some exercises to solve. From exercise 1, let's pick these two. Now we have the integration of 1 over 4x plus 5. The function is in the denominator. Of course, we can't integrate each term alone here. We have this as a full bracket in the denominator. So we have to rewrite this as 4x plus 5, that's the bracket, and taking it upwards, it will be raised to the power of negative 2 dx. Now we did a rewrite for the function, which will enable us to solve it. We know that if we have the function inside raised to the power of n, right, like this, and then we look for its derivative beside it. If it exists, we can directly, if the power is negative 1 like here, we say that it was the len of absolute of the function plus c. So what is left here is to get the derivative. Once we recognize that the function inside the bracket is f, it's better to write it down. F is 4x plus 5. Now what's f dash that I'm looking for? The derivative of that line is 4. So we need here 4 inside the integral. We would add 4, and of course, because we have no right to get the integration of 4 times the required function, we multiply by 1 over 4 at the same time, so as if we've multiplied by 4 over 4, which can be rewritten as 4 times 1 over 4. We take one of these two values inside and one outside, but overall we know that this is the value of 1. We take inside the f dash, which we need in order to be able to cancel it with that integral sign. So now what's will drop will be the extra 1 over 4, and we will solve the integral now, because what we have is the integration of f dash, which is 4, and then we have f to the power of negative 1 dx. And we know the solution of this integral, that it's equal to the len of the function. The function inside the power is the 4x plus 5. So as if the power is translated to the len, and then the function drops as it is. Let's move to part C. So part C, we have two terms in the denominator. Which do you think is the power of which? We know that we have the len x. The derivative of len x, if we're just thinking about it, is 1 over x, right? And the x in the denominator, we can see it at 1 over x, which is the x to the power of negative 1. So the derivative of the x to the power of negative 1 is we drop the negative 1 and we add negative 1 to the power to become negative x minus 2, or the shortcut that we talked about before, negative 1 over x squared. Okay, now is the term beside ln x seems to be its derivative. Of course, we know that this algebraic form, as if we have two terms in the denominator multiplied, we can separate them by the algebra as 1 over a times 1 over b. So this integration can be rewritten as one over x multiplied by 1 over the ln of x dx. Now we separated the two terms and both are kept in the denominator using this algebra property. And we have figured out that the derivative of ln is most probably the 1 over x beside, but the derivative of 1 over x is far away of the ln x, which is beside. The derivative of 1 over x is negative 1 over x squared. So 1 over x doesn't have beside something seemed like its derivative. But ln x, its derivative is 1 over x. And beside the ln x, we have the 1 over x. So we can now see this integral of expression. 1 over x is f dash. And we have here 1 over f. Yes, please notice that the function is still in the denominator. The ln x, its derivative is beside it, yeah, but it's still in the denominator. So we might rewrite it and raise it up to be with the power of negative 1. And therefore, we will say that we have now the f dash, which is 1 over x, and the f, which became of the power of negative 2, which is the ln of x, minus 1 dx. And because this is f and that's its derivative, we are ready to solve it. Now comes the time of the power. Now we consider the power. The power is negative 1, then it was the ln. It was the ln of what's inside plus c. What's inside the power here? Inside the power negative 1, we have ln x. We put it without thinking of it. So this ln outside is for the negative 1, the power negative 1. And it's ln of whatever inside that power of negative 1. It happened here that it was ln again. So we have the ln of the ln, absolute ln of x plus c. And this is the final solution. Let's get some different exercises from the sheet. I will get to that one. Now we have in part f, x over x squared plus 1. Of course, you know that the rule is having the f and the f dash both are in the same line. So one might think of rewriting this in one line form. So we have the x already up, x power 2 plus 1, we have to see it as one package, and we can raise it up. When it has no power in the denominator, we just raise it with the power of negative 1 dx. Now we suspect that the f is what's inside the bracket, right? So we suspect that f is the x squared plus 1. What would be f dash? F dash is 2x. Let's compare now the f dash and what's beside the power, the bracket with the power inside the integral. Yes, the x exists, but the 2 is missed. So we might add the 2 here for the sake of solving the integral, and don't forget to cancel its effect outside. Now after this analysis, we can take that here and we can say that it's equal to, we have 1/2, and inside the integral we have the 2x, which is f dash, and we have the f power of negative 1 dx. And we are able to solve this just by applying the rule Now the rule is ready to be applied, is the len of the modulus of what's inside the function plus c. So it's 1/2, and we have the len of what's inside. What's inside the power here? It's x power 2 plus 1. So we just copy it, and that's it. Very well. Let's move to part G. Okay. So in part G, here, we have again a part in the denominator and part of the function in the numerator. But watch out here. You have the len of x. And we know that the derivative of len is what? Is the 1 over x. And therefore, we need that 1 over x beside it. So let's just separate them. We know if we have a over b, this is equivalent to a times 1 over b. So I can take the len of x away and the 1 over x by itself dx. Now we can see that as we have a function and the 1 over x is its derivative directly like that. So the rule here is ready to be applied, and now we consider the power of the function. There is no power, then it's 1. So we will take the function, raise it to the power of 2, divide 2 plus c. The function here is what? Is the len of x. So yes, we will take the len of x as it is, raise it to the power of 2, divided 2 plus c. And that's it. Let's proceed to number H. So here in part H, we have a function inside and up and a function down. And of course, we might suspect that the function in the denominator, because it's of a higher power, it can be f, and this above function can be f dash. If that's the case, we have to double check this. So we have in the denominator this function dx. If we suspect that f is the x power 2 minus 4x minus 1, then what would be f dash? Directly we will drop the 2x minus 4. Now if you notice that the 2x minus 4, if you've taken 2 as a common factor, you will be left with x minus 2, right? And this is exactly what lies here beside the function inside the integral, right? So this is what exists here exactly. So it seems that that's really f dash, and then it misses the multiplication with 2, the times 2. So we can multiply by 2 and divide by 2 outside. So overall we've multiplied by 1, and now we can see the integral is 1/2, and the integral of f dash, which is now ready, over f dx. And we know that this form origin is the len of the absolute of f plus c. The f is the function in the denominator, so we say half len absolute f as it is, and then plus c. Very well. Let's move to part I. I will copy it here. So in part I, we have the integration of the len x over x multiplied by a bracket raised to the power of 5, and then we have 1 plus len power 2x. Let's stop at len power 2, this len power 2, okay? So this len power 2, you want to differentiate this with something else. If you have the power in the len, then you can rewrite it as len x all raised to the power of 2. And if you remember from the len properties, if you have len x power 3, for example, and the power is raised to the function inside the len, then you are able to drop it and rewrite it as 3 len x. So when the power is inside the len or over the len, this means that it's over the whole function. So here we have things in the numerator and the denominator, and between them there is a product. Let's recall from the algebra. If we have a over b times c, we can rewrite this as a times 1 over b times 1 over c. Also, we might take b and c upwards by updating the power with -1. Let's rewrite it. Then we can write ln x by itself. Multiply that x, we will have to keep it in the denominator, so it will be times 1 over x. And from without benefit, we have to keep it as it is 1 over x, because we know that that's directly the derivative of ln x. And then we, about the bracket, yes, the bracket we can take it upwards, because in all ways we suspect that this is the f, which is raised to the power, because it has a big power 5, which we are not able to resolve it directly. So we suspect that the f is what's inside the power, which is 1 plus ln power 2x, which is equal to 1 plus ln x, all raised to the power of 2. Now if we want to find the derivative of that, the derivative of 1 is 0. The derivative of a bracket power 2, we drop the power and we update it by 1. And then times what's the derivative of ln x, 1 over x. Okay, here comes now the comparison stage. We need to compare this with what's beside that bracket, which we called f. So the 1 over x is there. This is very good. And the ln x as well is there. And what's only left is the 2. And we know if the missing from the derivative is a number, we just add it and we cancel it outside. So we can say that this is equal to 1/2, and inside the integral, now we have the whole derivative f dash for the whole function, which is raised to the power of -5. We have taken that 5 upwards to switch the sign, of course, dx. And now we will consider the power, which is -5. Because it's not -1, so we will say that we will just add 1 to the power, -5 plus 1, which is -4, right? And then over -4. So this is -4 over the new power, which is -4 plus c. What do we add inside the brackets? It's the same function as it is in the problem without any change. So this is the solution. One might like to simplify the half and the -4. And we can simplify this directly to have -1 over 8. And then the 1 plus ln 2x, this is raised to the power of -4. And plus c, that's it. Let's go to, if this was I, we will go to j. Okay, how would we think of j now? We have a fraction plus another fraction. You remember when we say that the plus and minus are separators? So yes, we can integrate this alone and that alone. So in our minds, we see that we have this 1 minus x, and we can take it up directly to the power of -2, plus the integration of x minus 1, again raised to the power of -1 dx. We can transfer this one problem into 2 to get 1 minus x to the power of -2 dx, and then plus the integral of x minus 1 to the power of -1 dx. And this is in our minds or in our understanding, we don't have to rewrite it. So you can just directly integrate this alone and that alone. Let's do it like that. So if you want to integrate this, we suspect that what's inside the power is f. So if that is f, what is the f dash? The f dash is the derivative of 1, which is 0, and -1. So we need f dash to be beside this bracket. So we will add here times -1, and we have to add outside times -1 for that function only, for that bracket. So we see it as -1 multiplied by the integral of -1 and the bracket 1 minus x raised to the power of -2 dx. Now we know that this integration let's not add it here, okay? So we know now that this integration is a function raised to the power of -2, and this is f dash, and we have an integral and -1 outside. So this is going to be negative, and now considering the power, it's not -1, so we will add 1, -1 plus 1, that's -1 over -1. So overall, this negative would go with that one, and we will be left with the bracket raised to the power of -1. What would we add inside the bracket? Yes, exactly what was inside the bracket in the original problem. So this is part 1. We might call it I1. I for integral sub 1. What about part 2? Now in this bracket, we suspect that f here is the x minus 1. If this is the case, what's f dash? It's directly 1. And of course, we might imagine that it's multiplied by 1 and see that integral as 1 times the integration of x minus 1 raised to the power of -1 dx. And therefore, we have 1 also inside, so f and its derivative. Now considering the power of the function, which is -1, so its origin is the ln of the absolute plus c. And what do we add inside? Yes, it's the function. Now we can call this I2, and we call the whole problem I. Therefore, we have I is equal to I1 plus I2. The I1 was 1 minus x raised to the power of -1. One might like to rewrite it as 1 over 1 minus x, that's totally fine, plus I2, which turned to be the ln of x minus 1 absolute. And then we write 1 plus c for both of them. Each might carry plus c, yes, but at the end we will write it as 2c, which can be written as plus c, and that's it. Very well. Now let's take these two problems, and then we will be ready to move to the exponential integral. Here we have 6x power of 2 over x cubed plus 1, which can be the derivative of what? Of course, we suspect the function with the higher power. So here we know that x power 3 is of a higher power than x power of 2. So we will take this as a bracket, as a one package, as f. So we will say that f is x power 3 plus 1. Okay, in that case, what's f dash? We will drop the power, subtract 1, and the 1 will go away, so that's the derivative. If we need to compare this to what's inside, as you see here, we have the x power of 2. It's there. But the 3 is not there. We don't need the 6, so we can take the 6 outside. This is not the only solution for that. One might think in a different way. I will tell you about it later. So we might take the 6 outside, and then what do we need inside beside the x power 2 in order to continue the derivative? We need the 3 that arises here. So we would directly multiply with 3 inside and by 1 over 3 outside. Now we have outside 6 over 3, and we have the integral of f dash over f. And that was, if we've taken f upwards, it will be raised to the power of -1. So we can say 6 divide 3, which is 2. So we have here 2, and we can remove now the integration to write it as the ln of f absolute of f plus c. And inside the ln, we write the bracket, which we considered as f in the beginning. Okay? Very well. What I wanted to tell you is that when we find that the derivative is 3, I will not write it, I will just give a note to consider if someone of you thought about it. When the derivative is 3, you might rewrite 6 as 3 times 2 and take directly 2 outside, and you will have the 3x power 2, which is the derivative ready from one step. But it won't make any difference. But of course, it's a brilliant shortcut, or it's a smart way And we need to think smart in such problems. Okay, now in part B, we have the integration of 1 over x times root ln x. Again, we have two terms in the denominator, which we can rewrite them as 1 over a times 1 over b. This is very good. So we can rewrite this as 1 over x times 1 over, and inside the square root, we know that the square root is directly replaced by the power of half because we don't have the root in the rules of the integration. So we will say it's the power of half dx. Now, which is the function and which is the derivative? Of course, we can take the ln x upwards to be raised to the power of negative 1/2, the same power with the opposite sign. And now we suspect our suspicious here. F is the ln of x. Okay, what is f dash? It will be 1 over x, oh, that exists here. So we directly can solve this integral and remove this integration with the f dash, with the dx, and only the bracket drops considering the power, which is not negative 1. So we will add 1 and divide with the new power. Negative half plus 1, this is 1/2 divided by 1/2 plus c. What's inside the bracket will be dropped as it is. One might rewrite that 1 over half, because all of the half is in the denominator, we can rewrite it as 2, and the ln x, instead of power half, we can rewrite it as the square root plus c. Very good. So this for these functions. Okay, before we go to the word problems, let's get to the exponential integration. You remember the exponential function when we took its derivative, we said that its derivative is exactly as it is. The derivative of e power x was e power x. So if we have e power x, its derivative is going to be e to the power of x. And let's see this from the lecture notes. The exponential rule is here. We have the simple exponential rule. So if we're integrating e to the power of x, its integration is itself. If we have e to the power of function, we have to look for the derivative of the function beside. So this is what we need from the lecture as the rules. So again, let's translate this. If we have e to the power of u such that this u is the function in x, is terms in x, not just simply x to the power of 1, no, any other power of x, x power half, x power 2, x power 3, x power 1.1, and any other power of x. So we have here e to the power of fx, a function x. We look for the derivative of that function, only the function in the power. If it exists, we say that that was the derivative of e to the power f of x, and we add the integral constant. Here we have two functions and there is an addition. You know, the addition acts as separator. So inside our minds, we see it as the integration of e power negative x separately and the integration of x squared separated as well. This e is raised to the power of negative x. So f here is equal to negative x. What's f dash? It's negative 1. So we need here, beside the f dash as a coefficient. So we will rewrite it as negative 1. This is what we need as the derivative, times e power negative x dx. And of course, we don't forget to multiply by negative 1 upwards. The integration of that one is simple and direct. All what we do is a simple x power rule. So we will add 1 to the power and divide with the new power. And we do this as well if the power is not negative 1. So this is always what we are going to do. Here in the other part, which we didn't solve it yet, here inside the integral we have f dash and e to the power f. So in this case, we drop the extra minus 1, and this function inside the integral was the derivative of e power f, which is negative x, plus the part which we solved, plus c. Of course, this negative 1, it's not needed to be rewritten, so we might write it negative e power negative x, plus you can write it 1 over 3 x to the power of 3 plus the integral constant. Very well. Let's take that part. Here we have inside the integration 2e to the power of 2x. Again, if we have any function in the power, this is in the power of e, this is what we call f. What's f dash? It's simply 2, and it exists beside it. So we can solve this integral at once, and we can see it as f dash times e power of f. And therefore, this is the derivative of e power f plus c. So we can say that this integral is equal to e to the power of 2x as it is plus c. And that's it. Now, let's consider part E. In part E, we have e to the power of negative x squared. So f here is what's in the power of the e. E is 2.7. You remember? It's the irregular irrational number 2.7 blah blah blah. Now it's raised to the power of negative x squared, and this is what makes us recognize this as an exponential function and not any other type of function. We have studied that in the previous chapters. So if f is negative x squared, what would be f dash? We would drop the power and subtract 1. Perfect. What's we can find beside it? We can find the x, yes, but the number is different, so we can directly take it outside, this number which we don't need, and we add or multiply with the number that we need, and we cancel that outside. So here we would add the negative 2, which is required, and divide by negative 2 outside. So it's 9 over negative 2, and this is the derivative of the e to the power. That's it. So again, we fix the derivative of the power of e beside it. If we can do it, once we do it, we say that we solved the problem. Let's take these three together. Now we have e to the power of root x, that's part K. Part K, we have roots, and of course we don't have roots in the rules. We need to resolve these roots into powers, so we have e to the power of x, and instead of the square root to be to the power of half, over x, instead of the square root, it will be raised to the power of half dx. Now we know that when we have e to the power of f, we need f dash beside. So let's rewrite this as the integration of e to the power of x power of half, multiply this power in the denominator. If we have 1 over x power m, this is raised as x to the power of negative m. So we can multiply with x power negative half dx. Now we need to make sure that what's beside is the derivative of the power of e. So we say if f is x to the power of half, what's f dash? We drop the half and minus 1, it's going to be negative half. Now we find that the negative half, the x to the power of negative half, yes, it exists. What we need is the half. So we would multiply by 1/2 and multiply by 2 outside. And then we have e to the power of function times the derivative of the function, so we can get them both outside of the integral to be e to the power f. The f here was the x power of half, so we will just write it, or write it square root of x plus c, and that's it. Now if you want to make sure that this was the function where this one inside the integral was its derivative, this is called verification. Sometimes from time to time we need to do this if we feel that we are not sure of what we did. So we can just do it beside, if we have this, which we got outside. So if we took that and differentiated with respect to x, the 2 will drop as a constant. E power something will be itself times the derivative of that thing. The derivative of x to the power of half is half x power negative half. Now simplifying this out, we can remove the 2 with the half, and we will be left with x to the power of negative half, right, times e to the power of x power of half, which was really inside the problem here, what we rewritten in blue, or what's found here. So what we did was correct. You can do this in order just to recheck your solution. Okay, what about part L? L, we have again e raised to the power of a function. So directly we go and think of that form. This is what we think. We need e to be to the power of something direct, and in order to be able to search for its derivative. So here e to the power of x power 3, and all is raised to the cube root. Of course, we would think of getting rid of that cube root, and if we have the cube root of something, we just replace it, we replace it with the power of what? This is the cube root, and this is replaced with the power of 1 over 3. So we have here e to the power of x power 3, and all is raised to the power of 1 over 3 dx. Now do you remember when we had a power inside and a power outside? What was that? Yes, we multiply the two powers in the numerator. So we will say it's x to the power of n times m, right? So here we can rewrite this one more time to be x squared power 2 over e to the power. If we need to multiply what's inside with 1 outside, let's multiply x power 3 with 1 over 3, and this is going to be what? X power 3 over 3, right? So what we have here is x power 3 over 3 dx. Now we have e to the 1 power, and this is what we needed in order to be able to see the f of x, but still it's in the denominator. So we would like to take it upwards beside the x squared to be e to the power negative x power 3 over 3 dx. Now we know that we can take this. We know that f is the negative x power 3 over 3, or the negative 1 over 3 times x power 3. We do this separation. If we have a over b like we did before, we rewrite it into that. Or we might rewrite it into 1 over b times a like this. So now we had in the denominator a number. So this way we can separate the number from the x which we request to differentiate here. In order to drop the negative 1 over 3 and then differentiate x power 3 as 3x squared. And now simplifying this out, the 3 would go with the 3, and we will be left with negative x power 2. This is what we did here is the derivative. So here we got the derivative, of that form, that was f dash for this f. What's beside this exponential function? We have x power 2 and we need the negative, so we will add negative inside and outside. The negative outside will drop, and now we are ready to solve this integral and say that it was the exponential with its power as it is, plus the integral constant. So now this is the solution. It's e to the power of the function. What happened to the derivative? It goes away with that sign, with this dx. And what drops is the constant outside, the extra, and the exponential with its function. At any time, if you messed up or you feel that you're confused, try to differentiate that form. You will reach one of the forms that we have reached here. So that form or this one, you might rewrite it into that form, I mean. Okay, let's move to part M. In part M, we have the integration of 1 over 1 plus e to the power of x. What is that? We might try to think of 1 plus e power x because we can't separate them. We can think about it as f, 1 plus e to the power of x. But what would be f dash then? 1 is 0. Its derivative is 0 because it's constant. E power x's derivative is itself. Now, is any of the derivative exist here? Can we multiply by e power x up and down like we do? Now we can get around this problem, and this usually happens when we have e to the power of x and we need to find another e to the power of x because the function and its derivative is the same. So we need the function. One of the ways that we can solve it, we can multiply by the negative exponential up and down. So if you multiply it by e to the power of negative x over e to the power of negative x, that is 1, right? And we can separate them like we do to be e power negative x times 1 over, and then we will use this in our integral to multiply with e power negative x, which we need, over e to the power of negative x times 1 over 1 plus e to the power of x. And now pay attention. If we multiply with a function, we can't take something outside the integral. We can't take it outside the integral because we are integrating with respect to x. So it means that x can't go outside. It has to, this factor has, or this operator has to be applied over it. Now let's do a simple multiplication with this new idea. The numerator times the numerator, so we have here e to the power of negative x, and the denominator we would distribute this inside the bracket to have e to the power of negative x times 1 plus e to the power of negative x times e to the power of x, right? And when we have the same base, we can rewrite them with one base, and the multiplication turns to addition. Negative x plus x, yes, that's e to the power of 0, and anything power 0 is 1. So I will write here plus 1 dx. Now if we suspect this bracket in the denominator as f e to the power of negative x plus 1, what is f dash? It's e to the power of negative x times negative 1, and the derivative of 1 is 0. Now the derivative does exist. The e to the power of negative x does exist there. What is needed is the negative, so we can add negative inside and at that time outside. So this will be rewritten as negative, and in the numerator we have the f dash, in the denominator we have the f, the full bracket. dx. The final step was to consider the power of the function. Here f is in the denominator of no power, and we see this as power of 1. So if we raise that up, it will be to the power of -1, yes, which is the len. So we have here the len of the absolute of whatever was the function plus c, and that's it. Let's write inside the len here, we have the f, which is to the power of 1. So it's e to the power of -x plus 1. If you get any idea and you would like to apply it and make sure of it, you can come and double check it with me at any time. So this is one way of solving this problem. It's a new idea and we will consider it. Now let's move to the word problems. We have two word problems here in that exercise. Suppose the marginal profit for producing X units of a product is given by the function, this function, where P represents the profit. You know that the capital P is the profit, right? If it was small p, the small p is the small p is equal to the price, right? Or the demand. But the capital P is equal to the profit. This is according to the economy and finance. So where P represents in thousands of dollars, this is very good. Find the profit function. If we have the dP by dx, can we get the P? Can we derive the B from its derivative? Yes. If it was multiplied by 2, we would divide it by 2. If it was plus 3, the profit plus 3, then we will subtract 3 in order to obtain the profit. Now the profit is having this operator, the differential, d by dx. So we would apply its opposite, integral. So let's replace the dP by dx with the given function. Usually it's a simple one, minus 3x plus 150 dx. Now we have minus and plus around the terms, so we can directly, yes, integrate this. We have x power 2 over 25. When we have something over something else, we can take the 1 over b away of the a. This is by algebra. These two expressions are equal. And because here we have x power 2 over 25, we need to take 1 over 25 away of the x power of 2, because this is the expression that we integrate. So we can have 1 over 25 and integrate the x power 2. It will be x power 3 over 3. The power is not -1, so we add 1 and divide. Minus 3 again will drop. Now what's the power of x? It's of no power, then it's 2. We add to the power 1 and divide. That's the integral of x. And then plus 150, when we have a number alone, we just attach the x plus c. One might like to rewrite this in a better way. We would have here 3 times 5, which is 15. 5 carry up 1. 3 times 2 is 6, with the 1 is 7. So 1 over 75 multiplied by x power 3 minus 3 over 2 times x squared plus 150 x plus c. This is the profit. Now we have the profit, but not an exact function for the profit. We have a function, which is the x power 3, 1 over 75, x power 3 minus 3 over 2x squared plus 150x plus c, and c can be any constant. Usually in our word problems, they would give us a key in order to get that integration constant, which we call it the initial condition. And the initial condition is simply a specific value for x and its corresponding y over the given function. The y here is p, right? And the x is x, so we need x1 and its corresponding p1 given in order to substitute here and get the unknown, which is c. Also, it's beneficial in these problems to recall the integral constant as k in order to get away if you are solving for the cost to mix them up. Okay, find the profit function assuming that selling no items, what is the number of items? It says here that producing X units of a product. So X units of the product, this is the number of products. So that's why X is the items numbers. Selling no item, this means that X is equal to 0, results in a loss, and loss is a minus of this amount. So it seems that they want to tell us that if we sold no items, this will reflect to the profit with a loss of the $400,000. So we can go to that function that we derived here for the profit, and we can now directly substitute what? We substitute for the X 0, so this will be 0, and that is 0, and this is 0, and now the K is what? The corresponding B, which is negative 400,000. So from that, we know that the K is the negative 400,000, and we have derived now the full profit model, which is what? Which is that P, the profit, is the 1 over 75 x to the power of 3 minus 3 over 2 x to the power of 2 plus 150x, and then minus the 400,000. And that's it. Perfect. In part B, we need to find the cost if the marginal cost of a product is given. So again, we need to find the cost given that the cost of producing 13 units is 100. So we know that the cost of producing this amount of units, which is denoted by X, this is the cost in dollars, so that's the capital C. So as if we're given a point, which we call the initial condition, we have for X, its corresponding C, which is the 13, and its corresponding 100. So here, if we need to deduce the cost from the given d by dx of the cost, we directly just substitute. So now the cost is the 12 over the cube root of that function. Let's rewrite it with, and instead of writing the cube root, we will transfer it directly to the power of 1 over 3. Now, of course, the function inside the power is the function we suspect as f. What about f dash? It's directly 12. Oh, and it's found here. So we can rewrite this or just see it as f dash over f raised to the power of 1 over 3. Of course, you don't have to rewrite it like this. We are just discussing it together. But you can directly say that this is, yes, according now to the power, which is not negative 1, I will take the function, add 1, so 1 over 3 plus 3 over 3. This is going to be the 4 over 3. That's the 1. This is the new power divided by 4 over 3 plus k. Don't write it c here because we're in a problem of a cost. And then what's inside is as the function or as inside the bracket here, which was the 12x plus 1. Of course, one might rewrite this as 3 over 4, and the 12x plus 1 will be raised to the power 4 over 3. And we have here the cost plus k. And what can we do in order to get the k? Yes, we just substitute the x by 13 and the c by the 100. And therefore, we'll get the value of k as 56 0.35, and here we can rewrite the model as it is, complete model as the 3/4 and then the 12x plus 1 all raised to the power of 4/3, plus instead of the k we have the 56.35. And that's it.